Hi, I'm Strogatz, and this is a short presentation of our recent work titled Exact Finite-Dimensional Reduction for Population of Noisy Oscillators, and it's linked to Antonsen and Watanabe Strogatz theories. This is work together with Professor Pikowski at University Potsdam and was just published in Chaos. And the work was supported by a DFG grant. So we consider phase oscillators coupled in the first harmonic that can have either Cauchy white noise or Cauchy distributed of natural frequencies. We consider large ensembles, namely the thermodynamic limit, the number of oscillators going to infinity. And we describe an exact six-dimensional reduction of the dynamics, which as special cases includes the Antonsen ansatz and the Watanabe-Strogatz theory. We then show examples of why this is useful, namely now we can consider arbitrary initial distribution of phases and evolve it exactly in time within this low-dimensional description. And this also provides some options for perturbation theories. And also we're going to say something about the stability of the Antonsen manifold. So we take first harmonic coupling, which we write generally like this, that the phase phi j evolves or grows with the natural frequency omega j and is coupled via a force h, which can be in general complex. That's why we take here the imaginary part of it. So in this way, it's a very general way of writing first harmonically coupled phase oscillators because it can include many models. In particular, if we consider the Kuromoto model, which we know here on the right-hand side should be the sign of the difference of phases, then all we have to do is consider that h is now proportional to the first Kuromoto Daido order parameter, or the first moment of the phase distribution. So here h can first of all be an arbitrary function of time, but can also depend on the parameters of the system, so the order parameters, I mean. The same holds true for omega. Omega can in general be a function of time and can also depend on the order parameters. So it's a very general way of writing the dynamics of oscillators. Other examples that one can describe like this are theta neurons, which through extension can describe quadratic integral fire neurons, but also Josephson junctions can be considered, and so on. So I also said that we're going to be considering the thermodynamic limit. That means that instead of considering a couple of, a few coupled oscillators like this, where we talk about their phases, we now have so many that it doesn't make sense to talk about individual phases, but rather we have to talk about the probability density of the phase on the circle, like this. So the typical thing one then does, if you have the phase equation, you can write the kinetic equation for the probability density. In this case, this is just the continuity equation. And then if one expresses the density with its Fourier representation and plugs it into the kinetic equation, one gets a set of ordered differential equations for these moments Zn. These moments Zn are also the Kuromoto Daido order parameters of the distribution, or their Fourier modes of the probability distribution. Now, when we add noise, here I denote in green the Cauchy noise, or Cauchy distributed natural frequencies, both of these terms actually correspond to the same dissipative term here on the right-hand side, which is minus gamma, which is either noise strength or the width of the frequency distribution, times so it's a homogeneous term, Zn. If you want to know how this term comes about from the Cauchy white noise, there's a paper by Tonias and Pikowski. And actually for Cauchy frequencies, this was already argued by Ott and Antonsen in their seminal paper. And this is going to be our starting point now. So we're going to take these equations for the moments, which are exact, and we're going to now reduce the dimensionality of them. So let's first review the known dimensionality reduction techniques that were used. Probably the most famous is now the Antonsen ansatz. It describes a two-dimensional invariant manifold, but it's a specific manifold. So one has to start on this manifold for the evolution to be exact, otherwise just an approximation. It allows for a frequency distribution, or also noise, and it's valid in the thermodynamic limit. And there are even reasons to say that the manifold is stable in certain situations, as already argued by Ott and Antonsen. But what's also very important is that it just makes the system easy to integrate. It gives us one complex equation and we can describe the dynamics with that one complex equation. Okay, that's why it's very popular. On the other hand, so we have the Watanabe-Strogatz theory. This actually predates the Antonsen ansatz by quite a bit. It gives us three-dimensional dynamics that are exact, but now also for any initial condition. So one can start with an arbitrary distribution and evolve it in time with these 3 dimensions. It requires the oscillators to be identical, so no distributed frequencies, and also, of course, there can be no noise. Additionally, it describes any number of oscillators, which includes also the thermodynamic limit. And the integration always requires this n-3 constants of motion, so maybe it's not as simple as in the Antonsen case. Now, we combine these 2 theories, we generalize them in a way, we take some things from each of them. In particular, so now our description is going to be 6-dimensional. It's going to allow for any initial distribution. This we're going to take from the Watanabe-Strogatz theory. It will also allow for the frequency distribution or noise. This is something that before only the Antonsen ansatz could do. And it's valid in the thermodynamic limit. And it's also fairly easy to integrate. So now we get 3 complex equations. Of course, it's more than the Antonsen case, but it's rather elegant to also integrate. So in order to show how we do it, we're going to be needing generating functions. This is just a tool how one can deal with a large number of variables at the same time. So instead of dealing with an infinite set of variables, then maybe we want to put them all in one function, and then we just have these functions. Then there are 2 types of generating functions that we're going to be using. So one is the ordinary generating function, where here on this side we just have k to the power n, and the exponential one where we divide the whole thing by n factorial. These are commonly used. Here we're going to need both of them. Okay, so just as an example, if we take now our system of infinite set of ordinary differential equations for the moment z, we can describe the same thing with one partial differential equation if we consider the generating function. Okay. Now let's review the Antonsen ansatz. It essentially is a simple ansatz that says, what if the nth moment is actually just the nth power of some quantity? This quantity here we're going to denote by q. And it turns out if one plugs this ansatz into the system of equations, then every single one of the equations is just the same. And namely, it's the Antonsen equation right here. So all the equations are satisfied, and the dynamics follows exactly this equation. Just a view of how this looks like in terms of generating functions. If we consider now the exponential generating function of the moments, then the ansatz just means that this function has an exponential form. All right, we already made an extension to this in our previous work that was published in PRL this year. And this is easiest to see in terms of the generating function. So as I said, Antonsen ansatz says that the generating function has exponential form. Well, we allow it for another general function, beta, to come here on the right-hand side. If one considers this ansatz, plugs it into the equations, one gets a different set, or so a different partial differential equation for beta, or a different set of ordinary differential equations that at first sight doesn't seem to be any different. Why would one use this set instead of this set? But if one looks carefully, there's quite an important difference. Namely, so if you look in terms of the generating functions, with the moment z, there on the right-hand side here comes an underived term. While with beta, all the terms on the right are derived. So this is the derivative in terms of k. Yeah, and this is the second derivative in terms of k. Why this is important, I'm going to show in the next slide graphically. So if we write out the system of moments equation by equation, we see that on the right-hand side we have a homogeneous term, and then we have a term with index 1 larger. This couples higher moments to lower ones. And then we also have the term with index 1 lower. So this will be n-1. So the second moment is coupled to the first one. This couples the low moments to the higher ones. And this means that now we have the moments are coupled, and there's no way to just consider some of these equations. without making some kind of approximation. Well, on the other hand, if we consider now the beta system, notice that we have the homogeneous terms, yes, and we have the terms with index 1 larger, but none of these terms with index 1 smaller appear. This means that if for a certain initial condition, let's say, some of these variables are 0 from some point on, let's consider that beta 2 is 0, beta 3 is 0, and all the higher betas are 0. Notice that the evolution will not generate them. They will remain 0 for all time. And that means that now the first two equations are just the exact evolution from their point there on. Yeah. So this describes then a set of infinite, so an infinite hierarchy of invariant manifolds, because one can just truncate this system, and from there on out, this is an exact evolution. Okay, and now we go even further. We show that these manifolds are in some way related, or rather these beta variables, they cannot be completely independent. The dimensionality cannot be arbitrarily large. In fact, it can only be 6-dimensional if we have all the elements that I mentioned. So in our previous work, we went from the moments to these beta variables. Now I'm going to take you 2 steps further to alpha variables and then finally mu variables. Each time taking one term out, and in the end, we're going to end up with something that does not depend on time at all. It's an integral of motion. Okay, so in terms of indexes, with Z, with the equations for moments, we have index n, index m minus 1, and index m plus 1. With betas, we lost n minus 1, we have only n and n plus 1. And then in the next step, we're only kind of going to have n plus 1. And in the next step, we're going to lose even that. So starting with beta equations, first we have an ansatz, which is just so a power hierarchy of some variable y, and we introduce a new variable alpha here just temporarily. We plug this into the equations. We see that y has to have this kind of evolution, and now alpha are these variables that essentially on the right hand side you only get the term m plus 1. Okay, so now we're in this stage. The next step is the important one, and it's kind of hard to introduce if we don't have the generating functions. Namely, now I'm going to introduce the ordinary generating function of these alpha variables and write the evolution for it. And now comes the ansatz in terms of the generating function. Suppose we now define function mu like this with respect to the function alpha. We have here variable s that we just introduced. It's exactly this quantity right here, so the evolution of s. And if one now tries this and writes out the derivative in time of m, works out all the things, it just cancels. So in other words, now the m is a constant function in time. It's an integral of motion. Yeah. If you want to think about it, okay, this is in a sense kind of a generating function, so one could consider these small variables mu. These are now the integrals of motion. What are the dynamics that we gain from this? So apart from the Antonsen equation that we already took out, now there's an equation for y and an equation for s. Now, what are the transformations that we had to do? So there was an ansatz from beta to alpha, and there was an ansatz from alpha to mu. Putting that all together, we see that, so we went from the moment equations to these 3 complex equations plus a constant function mu. All the transformations that happened, so from moments to beta variables, this is a modified binomial transform. From beta to alpha, this is just a power hierarchy. From alpha to mu, this is expressed in terms of these ordinary generating functions. And then altogether, of course, we want to get back from these dynamical variables here and this constant function to the moments. And this is then described with this kind of transformation, which here can seem quite daunting. But in practice, one only needs a few of these order parameters all the time. Let's say if the coupling is not with very high moments, then the first few are quite easy to compute. For example, the first moment Z1 is just the combination of Q and so the function M multiplied by Y. Okay. Now, what kind of initial conditions must we set for this to work? Here we have a choice, just like in Watanabe-Strogatz theory, where one can choose how one defines the integrals of motion. Here also we have that choice, but maybe the simplest one to consider is just to say Q initially is going to be 0, S is going to be 0, and Y is going to be 1. Why this? Because for this particular transformation, we just have the identity transformation. So essentially, initially, the moments are equal to beta variables, are equal to alpha variables, and are equal to mu variables, which are the constants of motion. So then if one wants to define this constant function, well, it's just one is the generating function of initial moments, and that's it. Another thing that can help with computing this constant function is that it's linear with respect to the distribution. What I mean is, if a distribution has two components, let's say distribution 1 and distribution 2, they don't have to be distribution, but these two components, and each of these components, we know what function m it corresponds to, then the final m is just exactly the weighted sum of both of them. Yeah, so it's linear in that respect. This helps because if now we know the m for one distribution and m for another distribution, we know the m for the sum of these two distributions as well. Okay, and now what we can do with this? Well, the first obvious thing is we can now take an arbitrary initial distribution of phases, certainly not on the Antonsen manifold, we can take any. We just have to compute this function mu, and we from there on can have an exact evolution. Examples of these more exotic ones certainly is, for example, the half uniform distribution, yeah, which I note here on the circle or on the line would be like this. So it's uniform in some interval and 0 in some other interval. Or for example, one consider the sawtooth distribution like this. Yeah. So for example, there are examples in the paper of how mu looks like for this distribution, but so for half uniform it's just the arcus tangens hyperbolicus. Okay. Now, we can also say something about the global stability of the Antonsen manifold. This was already argued by Antonsen and also others later. But maybe this representation is quite easy because one just defines some temporary variables, and one can essentially bound the variable y and say that y now decays at least exponentially with exponent gamma. So this is the upper bound of it. And why this is important, because if you look at it, y is actually the variable that tells us how far we are from the Antonsen manifold. If y is equal to 0, then all the moments actually do not depend on y and do not depend on s, and therefore we are on the Antonsen manifold. So y equals 0 is Antonsen manifold. And this tells us that when we have noise, Cauchy noise or Cauchy disputed frequencies, from any initial distribution, we're decaying to the Antonsen manifold at least exponentially fast with exponent gamma. Here's a numerical example of that. We just took some Josephson junctions and took 3 different noise strengths. So in red, noise strength 0, no noise. In blue, small noise strength, and in green, slightly larger noise strength. And indeed, what we see, so a decay here. So for the order parameter, of course, this just goes to a fixed point or a standing wave. But if you look at the evolution of y, we clearly see this exponential decay. It can decay also faster with a faster exponent, but this is now the upper bound that we've computed here. Okay, another thing we can do, we can consider a perturbation analysis. I'm going to show this on an example. So in this example, phase oscillators couple like this, such that we have bistability. This means that both the asynchronous state is stable and a high synchronous state is also stable. So if we start close to asynchrony, we're going to go to asynchrony and stay there. And if we start close to synchrony, we're going to go to this high synchronous state and stay there. It's important to notice that both of these states are, of course, on the Antonsen manifold because they're the final state. So asymptotically, Antonsen is stable. Now, we can introduce a perturbation to this distribution, namely, for example, that a portion epsilon of the phases is somehow reset with a different distribution. In this case here, I show for the first harmonic distribution in red. Yeah. So this distribution now obviously is away from the Antonsen manifold. We have some kind of perturbation. And some of these distributions now we can have an exact evolution of with our 6-dimension description. And we can then look for whether this perturbation will induce a switch from synchrony to asynchrony, or will we go back to the synchrony itself. So here, for example, we can compute the basings of stability, so the basing of switching from one state to the other for different portions of oscillator being reset. Also, if we now have no noise, if gamma is equal to 0, well, in that case, we know that this has to be equal to just the Watanabe-Strogatz theory, and indeed it is. So then the variables y and s are actually related. They can both be expressed with the quantity q and some other quantity theta, for which the dynamics we can show here. And this is exactly the Watanabe-Strogatz description, and the dynamics, of course, reduces to 3 dimensions. Okay, so the take-home message is, we were able to take the description in terms of the moments, which is, of course, exact description of the phase dynamics in the thermodynamic limit. And we were able to find an exact transformation of variables such that we have only 3 complex variables, 6 dimensions, and we get one constant quantity, which we can express as a function, or as, of course, an infinite set of constant quantities. Yeah, and the benefit of this is now we can consider an arbitrary initial distribution of phases and evolve it in time exactly. Thank you very much for listening.